Hello guys, I hope you're having a great time. So today I'm going to talk a bit about deep learning and security. This talk is called Fooling Machines and Fooling Humans. So deep learning is great and has achieved a lot in the past few years. We had a lot of examples of great success with deep learning, but now today we'll see the security part of it. But before anything, let me introduce myself. My name is Guillaume Sanchez. I'm a PhD student in deep learning at the LIS in the University of Toulon in France. And I'm also a software engineer for Hexaglobe in AI R&D. You can meet us in the hall 14, booth A16, if you have any further question. So, first we'll see what it means to fool machines and what we can actually do. Today, deep learning systems are used for self-driving cars, for medical diagnosis, for face recognition, for security, for porn and violence detection and all that. So they basically the eyes and ears of computers today. But what if we can fool the systems? What if we can circumvent this porn and violence detection system to be able to actually hack them and be able to to send porn on Facebook or on YouTube, for instance? So what's deep learning anyway? Deep learning is a set of detectors, a hierarchy of detectors. So say you have an image, and you send this image into a series of detectors. So the first detectors are actually detecting only small stuff, like small edges of different orientations, gradients, bright zones, darker zones, and all that. Then the next layer of detectors are going to aggregate and reuse this detection to detect bigger stuff, more abstract stuff. So for instance, if you have an horizontal edge, then a vertical edge, it can deduce that might be a right angle. And then the next layer, if it sees 4 right angles, well, it can deduce that's maybe a square. So this is a hierarchical process, and that's fairly complex. But today, we're going to take a much simpler model, and the argument will still hold anyway, and the demonstration will still hold. So let me introduce you Cypher10. This is a very famous dataset for machine learning. It's pictures of 32 by 32 pixels into 10 categories. So you have, for instance, planes and cars and birds and all that. And the challenge is pretty simple. I give you an image, and you have to tell me in which categories it does belong. So our model is super simple. It's actually not a hierarchy of detectors. It's only one. And you can see that those detectors actually make sense, because if you look at the car detector, for instance, you see a big red circle with a blue circle on top of it. And that's because in the data set, there's a lot of red cars, and the blue circle is for the glass, actually, of the car. And you can see the same logic applies for the frog detector, because the frog is, well, green, and then there is water or ground. And then if we want to classify an image, we take this image, we do some pixel-wise comparison with the detector, and if the pixel-wise comparison is good, then we predict with good accuracy that we predict with good confidence that that may be a car, and if it's not the good category, we have a pretty low confidence. So some researchers actually had an idea. What if you take a picture of a bus and try to subtract the pixel the bus detector wants and add the pixel that, say, an ostrich detector would expect? What would you expect to happen? Maybe you would expect to see your bus becoming an ostrich, something maybe between both. And actually what you get is that. The image haven't changed at all for human perception, but now the classifier believes with a lot of confidence this is an ostrich. And now the problem starts to arise, because our system believes that this is an ostrich, and a human obviously sees a bus. So we're having a problem there. And all the images in the third columns are actually believed to be ostriches. So this is a problem. You can also do that with abstract images. And all these abstract images are predicted to be some kind of objects with pretty good confidence. Like this is an electric guitar to a deep neural system. That's a problem. How does that work? Well, all the small changes you do to each pixel, they all add up. And also it's a more mathematically involved argument, but we're pushing the classifier outside of the training domain. Is that a problem? Well, one might think that if you don't share your classifier, if you don't share your model, what your detectors expect to see, you can't do. You can't apply this perturbation, and then you cannot create those adversarial examples. But actually, you can use another classifier to build your adversarial examples, and they will transfer to your model. So if I want to attack you, I can train my own deep learning system, create adversarial images, send them to you, and you will be fooled. So things start to be a bit problematic there. And if we learn anything from Game of Thrones, it's that no matter how bad things are, remember they can always be worse. So we can actually print these examples. And despite the inkjet, the printer errors, the inaccuracy, despite your camera mistakes and all that, even if the pixels do not add up perfectly, you can still fool the system. So you have an image, a picture of a washer right there, and in the two pictures on the right, our system believes this is a safe. That's a problem. That's a problem. But our self-driving cars are still safe, right? Because nobody is going to print a stop sign, like an adversarial stop sign, and paste it on real signs and to fool our self-driving cars, right? Well, welcome the adversarial patch. This image has been crafted by a deep neural network to maximally excite the neurons that detect toasters. And the thing is, this is such a strong stimuli for its deep learning system that it's basically blind about anything else in the image. So you have an image of a banana, and the classifier sees banana, and when you put the adversarial patch right beside it, now it believes with a lot of confidence that this is a toaster. And that's a problem. Because if you put the stickers on stop signs, the deep learning system does not see the stop sign anymore. You see there is no rectangle around the stop sign. It's basically blind. So what happens if you start driving cars doesn't see the stop signs? That's a problem. But the patches, well, if you're aware that they exist, you can still see them and remove them. So we would like something that is a bit more stealthy. And that's what those researchers managed to do. You can actually make a deep learning system believe the stop sign is a speed limit 45 just by applying those carefully crafted black and white rectangles. And we can go even further. We can go further. This is an adversarially printed 3D turtle. And this turtle, when the square is green, it means the classifier saw a turtle. When it's red, it's a rifle, and when it's black, it's seen neither. And when when this is a normal 3D printed turtle, well, the deep learning system sees always a turtle. But when this sees an adversarial turtle, it never sees one. But this is not a problem if you turn a turtle into a rifle, right? But if you do it the other way around, that starts to be a problem. You can go to an airport with a rifle. Your deep learning system surveillance will see that as a luggage, maybe, whatever you crafted that for, and your surveillance is dead. But you might think, well, I don't use deep learning for security. I'm not doing self-driving cars. I'm just providing deep learning APIs for my customers. So nothing can go wrong, right? Nobody really cares about the accuracy of what I'm dictating. Well, we can actually craft adversarial examples to use your deep learning system that you train for one thing. We can craft examples to use the system for an entirely other thing. So for instance, you provide me an imaginary classifier that detects among different breeds of dogs, of animals, of objects, and all that. But what I'm really interested in too is just counting a number of white square into black zones. So what I do is actually create some correspondences. For instance, a tench means 1 square, 2 squares is a goldfish, and all that. And so I create this weird background. I send my image to you. And if you tell me this is a white shark, I know there were 3 squares in my image. And that was for a bunch of other things with different models. So how can we counter that? How can we make our self-driving car safe? How can we make our surveillance system safe? Well, we don't really know. We have no idea. We have nothing that works yet. So this is a big problem. We know that adversarial training helps. This means putting some of those crafted examples, some of the adversarial example into the training set. We know that helps, but it does not counter it correctly. And if you want to play with it, there is a tool called Fullbox that works, that helps. With it, you can create your own examples and play with that. So this is a problem. And now, well, we've seen how to fool machines, but can we fool humans? Let's try that. Some of those pictures were created by a deep neural network. I'll let you guess which ones. All of them. None of these people is real. And you've seen it in the news. Some people were creating fake porn of celebrities. So that starts to be a real problem. That starts to be a real problem because for reputation, for all that, we can create content of anyone. But obviously, the internet is full of good people, and well, the internet is not about porn, it's about Nicolas Cage. So that's what you can get. We can go even further, and we had some people managing to turn videos of horses into a video of zebras, and back again. Who cares? Nobody. But when you start to transform guys into girls, or people into other people, now you start to care. Because the day where you wanted to just have a video call with someone to assess their identity, well, those days are over. They can make you believe you're someone else. And that can be really damaging, because now people can shoot a fake video of themselves as Barack Obama, as Donald Trump, say totally inappropriate things, and start some geopolitical conflicts. And there's a world of fake news, guys. What about the voice? Well, if you just use the system we've seen for the images, the voices are still safe. Well, guess what? They're not. This company, Lyrebird, managed to create anyone's voice with just 1 minute of sample. You take 1 minute of a Barack Obama speech, and now you can have anything said in his voice. So are we doomed? Well, some people are working to detect fakes. So a team from Adobe had this fake detection deep neural network where they managed to detect that, for instance, this baseball player was actually added into the image. Is that a solution? Not really. Today, we're using GANs, generative adversarial networks. And so you have a deep neural network that creates stuff, and you have another one that tries to distinguish between fake and real. And the game is fairly simple. The generators try to fool the discriminator, and the discriminator tries to become better and not being fooled. And that means that whatever counter you can think of to detect fakes, you can use it as a discriminator, and your generator will learn to fool it. So are we doomed? Well, yes. Enter the fake era. Enter the world of fake news, where fake news are actually not indistinguishable from reality. We have no idea how to detect that. We have no idea how to protect those learning systems against attack. So deep learning is a solution to many problems, and it's actually a lot of new problems also.